The chemist I've chose to highlight today is Dr. Charlie Wand. So, Dr. Wand got a master's degree from St. Hilda's College, part of the University of Oxford, in chemistry. He then went on to receive his PhD from the University of York, where he studied confined pneumatic systems, and currently he's serving as a professor at the University of Exeter, which he's done since 2021. Wand identifies as a bisexual transgender man, putting him a part of the LGBT plus community, and he does a lot of LGBT plus advocacy. So he's a volunteer with PRISM, which is a program at Exeter for STEM-oriented LGBT plus individuals to network and collaborate, because they're often excluded from heteronormative programs. Additionally, he's spoken at LGBT plus events for multiple universities, including, but not exclusive to, St. Andrews University, the University of Nottingham, University of Manchester. Additionally, he's a member of Tigers, which stands for the Inclusion Group for Equity in Research in STEM, and he's been quoted saying, "Being visibly queer in academia shows others that they too can be queer and still succeed." So he's received many awards. I'm just going to highlight the American Chemical Society Trailblazer LGBT plus Chemist in 2022, which is a pretty big deal. And then also he's been receiving awards back since he received the ExxonMobil Prize for Physical and Theoretical Laboratory Undergraduate Work back in 2009. Some inspiring aspects of Dr. Wand's life was that he transitioned from a female presenting to a male while completing his doctoral studies at York. This means he understands the experience of how people that look like women are treated in the STEM field, which gives him more empathy when working with his own students, and he also says that he kind of notices how women are treated in this field just because he has had that experience of being treated as a woman. Additionally, his transition influenced his decision to get more involved with outreach towards LGBT plus inclusion in STEM. I also really respect that he took a short break from academia after battling with mental and physical health struggles. This is becoming more common, but especially in the field of academia, which moves so fast in STEM and everything, it's very admirable that he took a step back and looked out for himself. This is kind of connected to this. This is just kind of a fun fact, but he enjoys cooking in his free time, and he says that he looks to cook at least one new recipe every week. I just think that's a fun, inspiring, humanizing part of his life. So my first connection between Dr. Wand's work and class content is the concept of solubility. So in 2018, he examined the solubility of large molecules in different solvents. In class, we pretty much only looked at the solubility of things in water, but I still think there's definitely a comparison to be made. This connects to our solubility chart and how we can determine how things are soluble in water. Well, he was just looking at how things are soluble in different solvents. So my second connection, Dr. Wand studied surfactants, I don't know if I pronounced that correct, I'm sorry, which are molecules with hydrophobic and hydrophilic ends, meaning water's attracted to one end and repels to the other. And he examined how salt concentration affects SLES, and he found high salt concentrations lead to the branching out and connecting of micelle structures. So while we were in lab, we did the molecular monolayer experiment, where we created a molecular monolayer, and that actually acts as a surfactant because on the molecular monolayer, the heads are hydrophilic and they're polar, while the tails are hydrophobic and nonpolar. So I just thought it was kind of cool how we both worked with the same monolayer and how we actually understand what a molecular monolayer is. For my third connection, Dr. Wand investigated how different paints interacted with iron oxide surfaces, and he actually found that paint sticks more to hematite surfaces than magnete surfaces. So I connected this to our class content of iron oxide and figuring out the charges on cations. So iron is a transition metal, which means that it can form multiple different cations with different charges. So I kind of demonstrated here on the slide how one would determine what iron's cation is in iron oxide. So we know oxygen is an anion with a -2 charge, and then we do our cross multiplication, and once you do the math, you find out that iron has a +3 charge. And for my last connection, Dr. Wan modeled the viscosity of polymers in different solvents using computer simulations. And viscosity is a fluid's resistance to flows. So, for example, honey has a higher viscosity than water. So while looking at the polymers, a polymer, which is a large molecule that consists of many parts bonded together, are actually held together by strong covalent bonds, which we spent Unit 8 learning about. So sigma bonds are very strong covalent bonds that are bonding together all of the different molecules within the polymer. So we kind of understand how polymers work, which is really cool and connects to Dr. Wan's research. So I hope you guys enjoyed learning a little bit more about this really cool chemist and how we kind of can understand his work. Thank you so much.